Okay, so we're in section 2.8. This is the last section in chapter 2, and it's kind of a part B to what we talked about in 2.7. So in 2.7, we introduced the derivative and talked about its relationship to rates of change. And in this section, we're still working with that same idea, but we're defining the derivative as a function in its own right. And this is really the way we're going to be looking at derivatives throughout the rest of the course. So in the last section, we gave this definition for the derivative of a function f of x at a specific number a. F prime of a is equal to the limit as h approaches 0 of this difference quotient. We also gave kind of alternative representations of this definition, but this is the one that we refer to the most often. Okay, now one of the examples we looked at in section 2.7 asked us to find the derivative of a function. I believe it was y equals the square root of x at some general number a. So it said find f prime of a when a is some positive number. It didn't give us something specific like a 1 or a 3 or anything like that. And when we did that, we ended up with an answer that looked like an expression in terms of a as opposed to some number. And that ended up being, I talked about why that was useful, because once you've evaluated your derivative and you get that expression that's in terms of a, then anytime you want to use your derivative to find the slope of a tangent line or an instantaneous rate of change, you just plug in whatever number you want to find that slope at, and you don't have to go through this entire derivation every single time. So that's how we're gonna start thinking about the derivative. Instead of thinking of a as a specific number in the domain of our function f, instead what we're going to do is let a vary. We're going to relabel it as an x and just assume that that x is any number from the domain of f without specifying. Okay, so instead of using a, you're going to be saying x now. F prime of x is equal to the limit as h approaches 0 of this difference quotient. Notice we replaced our a's with x's now. And what we're doing is, by saying f prime of x, we're looking at f prime as its own function. So that means when we're dealing with derivatives now, we're technically going to be looking at two functions, at least two functions. The original function f of x and another function which represents the derivative of f of x. And here's an example of a graph of two such functions. In this case, the blue graph represents some function y equals f of x. The red graph is f prime of x. So you can see that here and here. So once we know what f of x looks like, what is f prime of x? How does f prime of x relate to it? Well, remember, f prime is the derivative in our original starting point, looking at what the definition of a derivative is even talking about. It represents slopes of tangent lines to this original graph. Okay, so take a look here. We've got this blue curve, and there's several tangent lines that have been sort of sketched in here with their slopes indicated. Here, where this graph is decreasing, we see that this tangent line at this number a, at this point a, has a slope of -1. So that means f prime of -1, which, remember, f prime of -1, or sorry, not f prime of -1, f prime of whatever this x value is right here, should be a negative number. And notice the corresponding value on my derivative graph is negative. It's below the x-axis. So this part of the this part of my red curve down here, where all of the function values, f prime of whatever these values are, they're all negative. They're all below the x-axis. Every single one of those corresponds to a negative slope up here. Now notice we eventually get to a point where the blue curve levels out, which indicates that its tangent line would have horizontal slope, or in other words, m equals 0. The slope would be 0. That is where the derivative is going to have a value of 0. Notice it's crossing the x-axis. Now, as we move from this point B to this point C, the function starts to increase, and at any value in between here and here, we're going to see the slopes of those tangent lines being positive from 0 to 1. All of them are going uphill. They're all positive. And I see here 1 is definitely positive. That indicates that my derivative is going to be above the x-axis, because that's where the positive function values would live, above the x-axis. Okay. Now notice here, as I move from point C to point D, looking at my derivative graph, we're still above the x-axis where these function values are positive, but it starts to decrease. And what that means is that up here, as I go from point C to point D, all of my tangent lines will still have positive slope, but the slopes themselves are getting smaller. Notice we're going from 1 down to 0. Still positive, but now those slopes are decreasing as opposed to here where they were increasing. So again, that's reflected here. Being above the x-axis, my f prime graph is giving me positive values, but decreasing. Then I get to 0 again, which corresponds once again to a horizontal tangent line up here. My slope is 0, so f prime of x will equal 0 down here. Then we can start to decrease, so our tangent lines will be negative once again because they're all going downhill. And notice from here to the rest of my graph, all the tangent lines would appear to be going downhill. So the rest of my derivative graph is below the x-axis. And notice how it kind of dips and starts to approach the x-axis once again. Everything down here is negative, but becoming closer to 0 as I kind of go this direction, which is reflected in the blue graph by the fact that this blue curve, even though it's still going downhill, is appearing to kind of start leveling out around here, and we don't know exactly what happens past that. Maybe it gets to another horizontal tangent line somewhere out here. Looking at point P right here, P, it's showing that it has a slope that's approximately negative 2/3. So down here, on my derivative, negative 0.767, that's approximately negative 2/3. The y-coordinate of this point is going to equal the slope of the tangent line at this point. The x-coordinates will be the same, 3 and 3. Okay, so you're going to do a little bit of this in this section, comparing graphs of functions to graphs of their derivatives, because now we're thinking of the derivative as a function in its own right, and we need to be able to see how these two things correlate. It's really, really important. Okay. So here, we're going to do a couple of things. I have a graph set up, and we'll talk about that graph after we get past, this right here. We're given a polynomial. F of x equals x squared plus 3x minus 6, and we're asked to find f prime of x. So notice it's not like f prime of a in the previous section where I think of a as some specific number. Now we're just leaving it in terms of x. So by definition, f prime of x is equal to the limit as h approaches 0 of f of x plus h minus f of x, all over h, okay? This is equal to the limit as h approaches 0, x plus h, I'm going to plug that in here, so that's going to give me x plus h squared plus 3 times x plus h minus 6 minus f of x, which is just x squared plus 3x minus 6, okay? All over h. All right. Got some more simplifying to do. So this is going to look like the limit as h approaches 0. I'm going to expand this out. I'm going to distribute that 3. That's going to give me x squared plus 2hx plus h squared. Distribute the 3, I get plus 3x plus 3h minus 6. I'm going to distribute that minus in. Remember that those parentheses were important. Minus x squared minus 3x plus 6. All over h. Now, having done a few examples already in the previous section similar to this, what we're expecting to happen now is several terms in my numerator to cancel out. And we are also expecting all of the remaining terms that have not canceled out to have h's in them, because then that'll cancel with this h down here. Does that happen? Well, let's see. I have an x squared and a negative x squared. Those cancel. I have a 3x and a negative 3x. Those cancel. Negative 6, positive 6. Those cancel. What's left? 2hx plus h squared plus 3h. Those all have h's in them, so I can cancel my h's as well. And I have 2 plus h plus 3. That's all that's left. So this is equal to the limit as h approaches 0. 2 plus 3 is 5 plus h. Okay? I'm sorry. I jumped the gun a little bit there. I didn't see my own handwriting here. Let's be careful with this. So this is not plus 2h, it's plus 2hx. I forgot about my x there. So actually what I have is limit as h approaches 0 of 2x plus h plus 3. Okay? Now I have a polynomial and I can use direct substitution. Plugging a 0 in for h leaves me with 2x plus 3. Okay. Yeah, I almost botched that up. So as expected, because we're not plugging a specific number in here, we're leaving it in terms of x, our end result should be an expression in terms of x. So this is a function in its own right. F prime of x equals 2x plus 3. Compare that to the original function, f of x equals x squared plus 3x minus 6. Over here, I've graphed both of these functions. So the red function is f of x. The blue function is f prime of x. And let's see if we can notice the same relationships as we did on the previous page. So if you notice, right here, I'm going to single out a point. My f of x function, being a quadratic function, is the graph of a parabola. And our parabola is decreasing all the way until we get to this vertex right here, which would have a horizontal tangent line. All of the other tangent lines up until that point are going to have a negative slope. Okay, that means my derivative itself should be negative all the way until we get to this point right here. But notice that point, the x value of this point is also the x-intercept of my f prime function. So f prime of x is equal to 0 exactly when the slope of my tangent line in f of x is equal to 0. Okay, that's what we would expect to happen. And then once we get past this, as we continue moving to the right, all of my tangent lines appear to be having positive slope, and not only positive slope, but increasing slope. The slope seems to be getting steeper and steeper, which indicates that my f prime of x function is not only positive, but also getting greater and greater, corresponding to the slopes of those tangent lines. Okay? So that does what we expect it to do. We're going to do a couple more examples of finding derivatives of functions, but without having to investigate the graph every time. If you want, I would encourage you to take a graphing utility or Desmos, something like that, graph both f of x and whatever we get as f prime of x, and see if you graph those both on the same coordinate axes, if you see that relationship in these cases too. So here, f prime of x is equal to the limit as h approaches 0 of x plus h to the negative 1/2 power minus f, I didn't use f of x plus h over here. I just went straight to the function, so I should just say x to the negative 1/2 power instead. All over h. You have a couple of options here. One thing you could do is you could work directly with rational exponents. You don't have to keep things in terms of rational exponents if you don't want to, though. You can convert them into radicals. Really, either approach is fine. If you're comfortable working with rational exponents, do that. You're going to have to be comfortable working with rational exponents in this class because we use them all the time. But at this stage, if you want, you could rewrite this way. So there's no harm in doing this. X plus h to the negative 1/2 power is the same thing as 1 over root x plus h minus 1 over root x. Same exact thing. Okay, all over h. Now at this stage, I have a couple of things going on. I have radicals to deal with, but I also notice that I have these small denominators in this larger quotient here. So I'm going to clear out my denominators by multiplying this by root x times root x plus h. That would be the least common denominator here over itself, because we have to be multiplying by something equivalent to 1, right? Okay, what would that look like? Limit as h approaches 0. So if I multiply this through, then this root x plus h will cancel with that root x plus h and leave me with a root x there. Root x. Here, the root x's will cancel, leave me with root x plus h. So minus root x plus h. And this is all going to be over h times root x times root x plus h. Okay? Now I notice it's still not helping me a whole lot the way that it's written, because I can't use direct substitution yet. I successfully eliminated these smaller denominators, but if I try to plug in 0 for h, I'm still going to get a 0 in my denominator from this guy right here. So I'm going to do an additional step where I multiply by the conjugate of this numerator, root x plus h over root x plus root x plus h. Okay, what do we get when we do that? Well, again, my numerator is going to look like a difference of squares. So this thing squared minus this thing squared, it's going to be x minus x plus h. Okay, my denominator is starting to look kind of complicated, but I'm still going to leave everything in factored form. So it's going to be h times root x plus h times root x plus h. Okay? Now up in my numerator, I notice that I have x minus x. Those will cancel. And minus h is what's left over here. Okay? So let's think of that as a -1 out here. Once I'm left with that minus h, it'll cancel with this h down here and just leave me with the -1 that was up there to begin with. So this will be equal to the limit as h approaches 0 of root x times root x plus h times root x plus h. And I'm going to have a -1 up here. Okay, now that that h is gone down here, I can see that a direct substitution would not put a 0 in my denominator. So we have continuity, and we can do that now. What would that equal? That's going to equal -1 over root x times root x plus 0, which is just root x, times root x plus root x plus 0, which is root x. Okay? This is equal to what? Well, root x times root x would just equal x, and root x plus root x is equal to 2 root x. This whole thing simplifies to -1 over x times 2 root x, or 2x root x. All right? Now, I can leave my answer this way if I want to, but since I started with rational exponents before, I'm going to see if I can get things back into the form of rational exponents. This is the same thing as -1/2 times x times root x is the same thing as x to the 3/2 power. Again, you need to be comfortable with rational exponents in this class. Hopefully you can see where I got that from. But this thing here is actually the same thing as x to the -3/2 power. Okay? So even though this was an acceptable answer, I wrote it this way because this is more closely matching the form of the function that I started with, x to the -1/2. And the reason I'm intentionally doing this is because at the beginning of chapter 3, we're going to prove a bunch of shortcuts to evaluating derivatives. And the first shortcut, one of the first shortcuts that we look at, the power rule, is going to show me how to take this exact function and find this exact derivative, and it's going to take me all of 2 seconds to do it. There is a direct shortcut taking me from here to here that allows me to skip all of this work and makes a problem like this massively easier. But you have to be able to see it in terms of rational exponents, or else it doesn't work. Okay. I think I can squeeze in one more before we end this first video. So here's another function, f of x equals x over x minus 2. I want to find f prime of x here. Same idea. The limit as h approaches 0 of f of x plus a. I'll go ahead and write the function notation first. It's good to do that just because you're forcing yourself to see and write out the definition of the derivative over and over again. That helps commit it to memory. This is equal to the limit as h approaches 0 of x plus h over x plus h minus 2 minus x over x minus 2, and everything is over h. Okay? Again, I have a complex rational expression. So what I want to do is multiply my numerator and denominator by the least common denominator here, which would be x plus h minus 2 times x minus 2 over itself. Okay? This is equal to what? The limit as h approaches 0. From the cancellation that we're going to get here, I'm going to see x plus h. This will cancel. I have times x minus 2 there. And then here, minus x times, I'm going to get some cancellation happening here, x plus h minus 2. And then you'll recall in my numerator, I'm not going to multiply anything out. Or sorry, denominator. I want to leave this like this. Okay, that's how my denominator would go together. Now I'm going to expand things out in my numerator to see what's going to end up canceling out. So multiplying this out, I'm going to get x squared minus 2x plus hx minus 2h. Here, negative x is going to be distributed into everything. So I'm going to get a minus x squared minus hx plus 2x. All over h times x plus h minus 2 times x minus 2. And then we have a field day just canceling things out. So x squared, negative x squared, those cancel. Hx minus hx, those cancel. Negative 2x, positive 2x, those cancel. The only thing left in my numerator is a negative 2h. The h here will cancel with the h here. Now I have the limit as h approaches 0. Negative 2 is all that's left in my numerator over x plus h minus 2 times x minus 2. Even though I have a rational expression, you'll notice now that if I were to plug a 0 in for my h using direct substitution, I will not end up with a 0 down here. Whereas up here, because of that h, before we canceled it out, that would have given me a 0. So this is where I get to use direct substitution. I'm going to plug a 0 directly in, and I'm going to get this. Negative 2 over, plugging a 0 in for h will leave me with x minus 2 here, times another x minus 2 would look like x minus 2 squared. Okay? So that would be the derivative of the function that I had started with, x over x minus 2. Let's go ahead and stop this video here. We'll pick up where we left off in the next one.